this is module 2 of the 2015 paper, the Redox Equilibra question. All right. So it's asked to define each, right? So standard electrode potential of a half cell. What is the standard electrode potential of a half cell? We'll just do a few questions here and there, and then tomorrow we'll figure out everything else because, whatever. So, what's happening? We don't know the answer to this?
So the standard electrode potential of a half cell is a method of cathode aqueous solution um compared to a hydrogen cell under standard conditions, which is 298 Kelvin 1 atmosphere, and the what am I missing?
One.
Oh,
One more
the
per
1 mole per dm cube.
Okay. So the standard electrode potential of a half cell, right, is a voltage measured. So as it was stated, right, the voltage measured by the half cell, right, when connected to a standard hydrogen electrode, right, under standard conditions. 2 marks. The standard cell potential of an
Sorry, go again.
electrochemical cell. Okay, standard electrode of a half cell, right? So this is the potential difference measured, right, from a half cell. Should I say a half cell? We know what a half cell is, right?
Sure.
Standard hydrogen electrode under standard conditions. Alright. Okay, so that is the answer. Alright, so that's what we have there. Alright. The standard cell potential of an electrochemical cell, what is that?
It's the voltage which occurs when two standard half cells are joined under standard conditions.
Okay. Two half cells are joined under standard conditions. Lovely. All right. It seems really easy. Consider the following unbalanced equations, right? The following unbalanced equation, which describes the process that is taking place in an electrochemical cell under standard conditions. What will be the anode? Okay, by the way, now you look at your booklet
Okay, by the way,
and tell me what the answer is. Does anybody have a booklet? Send the booklet in the WhatsApp group if you have the booklet. But other than that, let's move on. Which one is more active? Go ahead.
Aluminum
And
solid
therefore aluminum will
reversible.
be what?
I'm doing the anode equation.
So we're saying that the more reactive metal will be an anode, yes? So go ahead with the anode
Mm.
equation.
The aluminum solid reversible arrows give aluminum 3 plus AQ plus 3 electrons.
right? So it's going to be Al3, well, 3 plus R 3 electrons. All right, and that would mean our cathode now, right? So we're gonna have to show anode is oxidation. Oxidation is the loss of electrons. Lovely, that is being shown. Here now we have our tin now plus, which is the gain of these electrons, are 2 electrons, right? That would now give us regular tin as a solid, of course. And everything, this must be equals AQ. I guess this needs to be, well, equals as well, AQ. All right, write the cell diagram. Let me check something. Draw the thing. Okay, what is the cell diagram? Remember anode before cathode. A, B, C, right? So at our anode, what we have, okay, so at our anode, what we have is aluminium, right? Al3 plus, right? Then we're gonna have SN2 plus SN. All right. So how do you do cell diagram notation? That should be it, right?
Yes, sir. B would be the salt bridge.
Yes, B would be the salt bridge. Okay. Oh, the thing I'm missing from these is the state symbols, guys.
Yes,
Forget
sir.
the state symbols. All right, moving on. One mark that. Oh, whoa, this is so annoying. All right, so we will just have to provide this now. All right, so let's have a go at this now. So we're gonna have 2 half cells, right? Aluminium in high resistance voltmeter, right? We're gonna have our salt bridge, right? So we have our aluminium over here. We're gonna have our tin over here, right? We're gonna have our anode will be our what? Our negative. Which what is going to be our anode is what? Positive or negative?
Negative.
So it'll be positive. All right, lovely. So we're gonna have a solution of Al3 plus present here. We're gonna have a SN2 plus present here, right? Let's say that our salt bridge contains our most lovely potassium nitrate, NO3, right? And let's say that our nitrate ions are going here. Technically, nitrate ions will go both places, but they didn't ask for the movement of that, so let's not overcomplicate it. So the thing is now, while you're doing questions, don't try to overcomplicate things if they never ask for it. Alright, so let's leave it like that. Alright, we have a bridge there. Okay, so what are we going to be labeling now? This is what? It's gonna be our high
High resistance voltmeter.
high resistance or high risk or high risk voltmeter meter, whatever that is, right? This would be our cathode. Okay, you know how you draw diagrams in biology? Having everything annotated to the right? That is how I draw
Yes,
my
sir.
diagrams, and that is why I prefer to see diagrams, right? So don't do that. Just try to label everything neatly on there, right? But here we have our salt bridge. right? And then I guess these are solutions are electrolytes. So this would be our tin electrolyte, and this would just be our Al electrolyte. Ele-
Sir, wouldn't we put the
Repeat.
one more per diem
Yeah, so it'll be
and
one
the
more per day.
298K?
So I would okay. So you could do that. So you could state the temperature, right? So you could state the temperature as 298 Kelvin. You could state the concentration of solutions to would be 1 molar. And you could state the pressure, right, to be 1 atmosphere. All right, that should be fine. That should give you your marks. And we're looking here at our electrode potentials given here. Ooh, how interesting! How how beautiful it is.
Wait, sir. Sir, could you please go back up a little bit, please? Where was the electron flow shown?
Oh, sorry, I didn't put the electron flow. My bad, my bad, my bad. Electron would flow for always from anode to cathode. So let me use a different color. Electron flow would be from anode to cathode. That makes sense now? That's electron flow. Always from anode to cathode.
Yes, sir.
Alright. Here now we have these reactions. Lovely. How interesting. Let's just have a look at it for 3 seconds. Okay. Right. Wait, what's the question? Did I scroll across the question? What are we supposed to do with this? Okay, okay, each electrode okay, value the okay, phone we need to find the E cell of this reaction. How you find E cell? E naught cell. We did it yet when we did the first marathon.
Sir, cathode minus anode.
Alright. Is the cath minus the anode. Alright, the cathode minus the anode. Lovely. Alright, so what's our cathode here? Aluminium, right? So we have aluminium, right? But let's look at our aluminium. What's happening to our aluminium? Let's go to our equation up here. Our aluminium, right, is actually here. Come on. You know you want to load. Alright. Our aluminium here is losing electrons, right? Right, guys? Right, guys?
Yes, sir.
Okay, lovely. So aluminium is losing electrons. Therefore, this value, we have to change sign to be positive 1.66 because that is the reverse. All right. Hopefully, we see that. All right. So our next reaction, our zinc is actually gaining. Therefore, this is actually fine as negative 0.14. Therefore, we're going to have the cathode, which is actually negative 0.14, right, minus 1.66, which is equal to,
Sir,
go ahead.
sir, can you go again while you flip the sign?
Okay, so what is happening to our our aluminum in the diagram? Our aluminum is losing electrons, right? So it is oxidation. What
Yes,
is
sir.
what is being shown here is a reduction. So what we need to do is get the EMF of the opposite reaction here. Because this is showing reduction, so we need to actually get the value for the oxidation. Alright? And then we flip the sign to get the value of our oxidation. Right? So that is what's happening there. If we didn't, what we're going to end up doing is adding 1.66, which is inaccurate. We're going to get negative 1.8. And what does that mean for us? If it is negative, that means that reaction is feasible or non-feasible. Which one?
It's not feasible.
Feasible.
Lovely. And that is the end of this question here.
Excuse me, sir, why do you have